Welcome to the debate. What if I told you that the local development server you use every single day is intentionally running 26 times slower than it actually needs to?
I mean, honestly, you'd probably have a lot of very angry listeners nodding along right now.
Exactly. If you're a developer listening to this, you've definitely experienced that sheer frustration of waiting 10 seconds for a local worker to spin up just to test a single line code change. For years, software engineers have just sort of accepted this massive latency just to ensure that our local environments perfectly mimic production. But today, we're looking at a framework that just throws that entire philosophy out the window. We're examining the architectural design and the structural trade-offs of local development substrates, specifically diving into XRanger, which is the local Wrangler-compatible substrate for the fork join and Aeon worker stack.
Right, and digging into this documentation really forces us to confront a highly contentious question in modern engineering. When we're building these local worker development environments, should our tools prioritize raw, bare metal execution speed and, formal mathematical verification, or should we prioritize strict, uncompromising sandbox emulation of the actual production environment?
Yeah, and this entire discussion emerges directly from the XRanger repository's documentation and formal specifications. I'll be defending the architectural shift we see here. I genuinely believe that moving toward bare metal native module execution and formal routing paradigms is a massive necessary evolution for edge computing.
And I take the opposing view. I argue that bypassing full isolate sandboxing, which XRanger explicitly does, by the way, risks the foundational utility of having a local environment in the first place, which is production parity.
Okay, let's unpack what that actually means for the developer on the ground. Standard Wrangler development environments, they run your worker code inside Miniflare and Workerd.
Right.
To give some context, that is a full V8 isolate sandbox. It is essentially spinning up a completely isolated, self-contained instance of the Chrome JavaScript engine for your code, layered with intense Cloudflare runtime emulation. And XRanger just entirely replaces that heavy machinery.
It throws it out.
Completely. It literally just imports the worker module and executes direct fetch calls. It passes the request, environment, and context directly into the module. And because it's backed by a Rust manager and something called Gnosis Shearing for its network ingress, the performance gains are, well, they're staggering. The UDP Aeon flow transport in XRanger achieves 57,188 requests per second.
Oh, wow.
Yeah. Compare that to just 2,179 requests per second in standard Wrangler dev. That is over 26 times faster. For local dev, for CI pipelines, and for edge-on-a-box deployments, this pure, unsandboxed execution path is just vastly superior to lugging around a simulated V8 engine.
Okay, look, that speed is undeniably impressive on paper, but I come at it from a completely different direction. That local-first boundary in XRanger is a critical compromise, and frankly, I think it's a dangerous one.
Dangerous how?
Because the source material explicitly admits that the 25x latency penalty in standard Wrangler comes directly from that full Cloudflare runtime emulation. But that emulation isn't a bug. That is a necessary feature to ensure your code actually works when you deploy it to a globally distributed network.
Well, but
Hear me out, because XRanger explicitly does not claim full worker parity because it relies on bounded, local-only durable object emulation, and because it uses mere placeholders for massive Cloudflare-managed families like message queues, R2 storage, vectorized databases, it creates a massive structural blind spot. You are building an environment where a developer's local tests will pass with flying colors at 57,000 requests per second, but the remote execution will just crash the moment it hits the realities of a true V8 isolate.
I hear that concern, but I'm just not convinced by that line of reasoning. Comparing standard Wrangler to XRanger is like comparing a heavy flight simulator with full weather physics to testing the raw aerodynamics of a wing in a wind tunnel.
Right.
Isn't the point of a local development substrate to isolate and test the worker code's core logic without the heavy, the envelope ceremony of the production engine?
The wind tunnel is a great analogy, but you have to consider what happens when the aerodynamics of that perfectly controlled wind tunnel completely fail to account for the actual chaotic atmosphere the plane will eventually fly in. Let's look exactly at how XRanger processes requests without that sandbox.
what the source material calls the honest path execution model.
Okay.
The documentation states that MTLS certificates bindings are carried through the configuration parsing. But the local runtime code explicitly does not claim end-to-end MTLS subrequest presentation, nor does it enforce the hyperdrive CA chain.
Right, it bypasses the certificate authority validation locally.
Exactly. And practically speaking, if you are writing a worker that securely connects to a legacy database that requires strict CA chain validation, XRanger simply ignores that complexity locally. Your local wing behaves perfectly in the wind tunnel, but to call this an honest path feels like a huge misnomer when the network behavior is fundamentally dishonest compared to the edge network where the code will actually live.
That is a fair critique of the term, yeah, though I would frame the architectural choice differently. Look at the specific workflow velocity gains the source outlines. Because of this choice, they show 30 times faster authentication token generation and 4 times faster KV storage get operations.
Sure, but
We're talking about an auth token being generated in roughly 2 milliseconds versus 60 milliseconds. We're talking about KV GEAT operations scaling to over 6,300 requests per second instead of 1,500.
at what cost?
At the cost of redundant local cryptography. You have to understand how XRanger achieves this. It uses a Rust manager leveraging Gnosis IOUring. For our listeners, IOUring is a feature in the Linux kernel that allows user space applications to talk directly to the network hardware, completely bypassing the traditional heavy context switching of the operating system.
Right, it drops the overhead.
Exactly. It provides a baseline hardware-level velocity that allows developers to iterate in true real time. If you force the local environment to do full cryptographic chain of trust validation on every single local loopback request, you are choking the CPU and reintroducing the exact latency XRanger was built to eliminate.
I have to jump in here because I just don't buy that argument. Let me tell you exactly why. Velocity is completely meaningless if your engineering team is running in the wrong direction.
Oh, come on.
No, seriously. The entire point of a tool like Hyperdrive, for instance, is to maintain secure connection pools to databases. If your local environment fundamentally handles connection security differently than production, what happens? A developer writes code, optimizes it for that beautiful 2-millisecond local response time, deploys it to the edge, and immediately hits connection timeouts or TLS handshake failures.
Well,
The developer's trust in their local environment is instantly fractured. They now have to maintain a constant mental state about what XRanger actually validates and what it silently ignores. That cognitive load entirely negates the milliseconds you saved on the request.
but those saved milliseconds aren't just a vanity metric. If you strip out that overhead, you free up the runtime to do things standard HTTP literally cannot handle. Which brings us to what developers can actually do with that bare metal speed, the introduction of the multi-lane transport.
Right, the multi-lane approach.
Yes, XRanger introduces a polyglot wire architecture. You have one single worker fetch handler, but it answers 3 different transports simultaneously: standard HTTP, TCP AON flow, and UDP AON flow.
Yeah.
And this isn't just about making standard web requests faster. This architecture allows upstream testing harnesses to fork, race, or fold payloads simultaneously across all 3 lanes, and the receiver deduplicates them by a content-addressed entity ID.
Wait, deduplicates them.
Yeah, meaning it hashes the payload, looks at the ID, and if it already received that data over UDP, it safely ignores the TCP packet. That is a massive paradigm shift in how we conceive edge networking.
A paradigm shift, undoubtedly. But I question the pragmatism of this for Wrangler compatibility, which is ostensibly the stated goal of the project. Let's look at the mechanics of these new lanes. The TCP AON flow uses 10-byte conscious tick frames. The UDP AON flow is explicitly MTU bounded, meaning the maximum transmission unit is capped at around 1,200 bytes per datagram.
Which makes it incredibly lightweight.
Lightweight, yes, but at the cost of standard web behaviors. Heavily optimizing your local environment for these bespoke AON flow protocols diverges wildly from how the internet actually works. Standard HTTP comes with about 450 bytes at headers. The CPU has to parse those strings, read the user agent, check the content type.
Right.
By skipping all that and just using length prefixed 10-byte TCP frames, you are dramatically changing the CPU load, sure, but you are essentially writing code for a totally different internet.
How is a developer supposed to guarantee their worker behaves correctly when deploy it to a standard web endpoint if they've been testing it against 10-byte TCP frames in a vacuum?
I hear the concern about protocol divergence, but let's look at what they are actually prioritizing from a different angle. The documentation explicitly states, local equals Rust over HTTP is king, over the web equals and diversity. If XRanger speaking all three lanes allows a deployed worker to participate on either side of that line seamlessly, isn't it expanding the definition of edge computing rather than failing to emulate it?
I'm not sure I follow.
Well, they are using a wire envelope that is pure JSON over base 64. It is dependency-free and bidirectionally round-trip tested. They aren't breaking HTTP. They are superseding it for machine-to-machine calls.
Superseding it how?
By removing the translation layer. The 1.4 to 1.5x speed multiplier you get on TCP and UDP over standard HTTP and XRanger is precisely because 0 bytes are wasted on envelope ceremony. The CPU isn't parsing text headers, it's just reading pure data. For latency-sensitive machine-to-machine invocations, being bound to a 1200-byte UDP datagram isn't a limitation, it's a feature that enforces highly optimized, predictable packet sizes.
It is a feature if you are building exclusively within the Aeon ecosystem. But if XRanger is meant to be a Wrangler-compatible substrate for the broader web, introducing a multi-lane transport that doesn't exist in standard Cloudflare architecture introduces immense complexity. And that complexity bleeds directly into how these bespoke lanes are actually secured, which brings us to the formal mesh policy.
Ah, the mesh.
Because you can't rely on standard web application firewalls for 10-byte TCP frames, right? So the documentation outlines a port-authenticated mesh with an incredibly intricate gate ordering system.
Intricate, but incredibly rigorous. The mesh policy has a strict gate order. First an overlay prefix match, then a path whitelist, then method allowance, and finally authentication. And this isn't just standard conditional logic. It is backed by lean modules.
We should probably clarify what that means for the listeners.
Absolutely. Lean is a functional programming language, an interactive theorem prover. When the documentation says 0 sorries, they mean the code has absolute mathematical proofs backing its logic. There are no sorry, just trust me assumed axioms left unproven.
Right.
We're talking about formally proven theorems like empty port list seals region or port overlay cancels within ports. It mathematically cannot fail the logic check. Furthermore, this entire policy compiles down to a .bw binary artifact. This gives developers an idempotent, deterministic deploy fingerprint, a content-addressed SHA-255 hash of your infrastructure policy. That level of rigorous formal security verification simply does not exist in standard Node.js-based local dev environments.
Look, that mathematical certainty sounds pristine, but I actually think you can use this complexity against the utility of XRanger. I look at this and see a system that is so highly over-engineered that it introduces entirely novel failure modes. Just look at the explicit anti-ice bypass surfaces documented right there in the source material.
You mean the intrusion countermeasure overlays?
Yes. The documentation specifically names the overlay hole bypass, the clock rate side channel, and the Xenonic approach. Let's look at the clock rate issue. The source refers to a mathematical state called deficit unbounded in Horizon. Basically, if an attacker can accumulate unobserved ticks simply because of a slight clock rate asymmetry between two servers, they can bypass the gate. To bring back your own wind tunnel analogy, you mathematically proved the aerodynamics in a perfect vacuum, but you forgot to account for the actual wind shear, the temporal desynchronization that happens in the real sky.
Okay, wait.
A standard web developer writing a simple edge function now has to comprehend clock rate side channels to ensure their environment is secure. It heavily fractures the usability of the tool.
Wait, let's unpack that for a second. Just because a side channel exists doesn't mean the mesh fails. It means XRanger has mathematically mapped the exact boundaries of the vulnerability. Take the Xenonic approach you mentioned. For anyone listening, this is based on Zeno's paradox, the idea that if you constantly have the distance to a wall with every step, mathematically you never actually touch the wall.
Right.
XRanger uses a denominator doubling contraction that ensures certain malicious requests literally never finitely land at the execution port. It traps them in an infinite loop of halving. By formally modeling that a barrier is never reached in finite steps, doesn't XRanger provide a far more transparent threat model than the black box security of standard local dev stacks?
I'm not denying the math is fascinating.
But it's more than fascinating. It's structurally superior. In standard local development, you just hope the underlying isolate engine doesn't have an unpatched vulnerability. Here, the vulnerabilities are structurally distinct and mathematically bound. When a defender layers an ICE, an intrusion countermeasure overlay, they know with absolute certainty exactly what vectors remain open. That isn't a bug. That is the very definition of security through verifiable architecture, rather than security through obscurity.
Transparency is highly valuable, absolutely, but we have to ground this in the reality of a developer's daily software engineering workflow. The source notes that if two agents deploy overlapping meshes on the same environment, it resolves by inclusion-exclusion. It proudly notes that deploy order is irrelevant due to the deploy order irrelevant theorem, and full containment collapses to the larger overlay.
Right, which prevents race conditions during deployment.
From a mathematical standpoint, it is beautiful. From an operational standpoint, it is a nightmare to debug. Imagine a request returning a 403 because of an overlay blocked reason. The developer now has to trace back through orthogonal security overlays, stacking additively, to figure out why their local environment is blocking a path that works perfectly fine on a standard Cloudflare worker. You've completely lost the plot. The tool is supposed to serve the developer, not force the developer to become an applied cryptographer just to run a local dev server.
But the tool does serve the developer by explicitly separating these concerns. You don't have to be a cryptographer because the TypeScript runtime delegate abstracts all of this math away. A developer doesn't need to write lean theorems. They just declare their mesh in the wrangler.toml file.
Yeah, but
If a port is absent, it means it's unrestricted. If it's present with 0 ports, it means it's fully sealed. It is incredibly declarative. And because it all compiles to a node-free TypeScript loader that uses native ATBO string decoding and runs natively on Cloudflare workers, Dino, Bun, or Node, the local execution is completely detached from the heavyweight constraints of worker emulation. You get a deploy-invisible artifact that behaves identically to the raw configuration, and this is proven by 60 specific behavior parity test cases in the source.
look, I don't disagree that the compilation to a binary.bw format is elegant. The deterministic nature of it, avoiding parsing TOML configuration files on the request hot path in production, is a fantastic optimization. But honestly, it all circles back to the core philosophical divide we started with. You are celebrating how abstract and cleanly separated the environment is from workered. I am arguing that separation is exactly what fractures trust in the ecosystem. When you rely on XRanger to simulate a remote preview through local deployment manifest, rather than actually hitting a real Cloudflare preview worker, you are guessing at reality.
Well, I believe it is a calculated and highly beneficial trade-off, if I can summarize my position based on everything we've unpacked today. XRanger represents a fundamental, necessary evolution. By discarding the heavy V8 isolate sandbox in favor of bare metal Rust and Gnosis-orient execution, developers unlock 26x speed improvements. They get local execution that processes at 57,000 requests per second.
Which is fast, yes.
Coupled with formally verified lean mesh policies and a polyglot wire architecture that handles HTTP, TCP, and UDP simultaneously, it provides a vastly superior modern foundation for edge worker testing. It strips away the pretense of emulation to deliver raw, verifiable utility.
And to summarize my stance, the abandonment of the V8 isolate sandbox and the lack of full feature parity specifically regarding critical security elements like end-to-end MTLS presentation and actual durable object network routing fractures the trust a developer places in their local environment. A local environment's primary job is to perfectly mimic production so that bugs are caught locally, not in the wild. By prioritizing raw throughput
and formal structural proofs over exact runtime emulation, XRanger forces developers to hold two entirely different mental models of how their code will behave.
Though we obviously view the fundamental philosophy of local environments differently, I think we both clearly agree that the technical achievements within XRanger are highly innovative. The deterministic BIW bundle fingerprinting, ensuring byte-identical outputs that deploy tooling can use to skip unnecessary redeploys, is genuinely brilliant.
Absolutely. And the multi-lane deduplication we discussed, where a receiver can take payloads raced over UDP and TCP and deduplicate them instantly by a content address entity ID, is a fascinating approach to mitigating network jitter at the edge. There is immense technical merit in this repository.
The core continued disagreement remains whether that raw throughput and those formal structural proofs are worth sacrificing exact runtime emulation. It highlights an inherent, perhaps unresolvable tension in software engineering. The eternal tug-of-war between iteration speed, formal mathematical verification, and environmental parity.
It really does, because ultimately every software abstraction is a choice about what details you are willing to lie about in order to move faster.
The lean theorems, the multi-lane networking paradigms, and the underlying bare metal architecture embedded in the XRanger material offer a deep well for further exploration. It leaves us back where we started. Do you want the blistering velocity of the tape on the bare floor, or do you demand the reality of the heavy costumes in the dress rehearsal? That is a choice every engineering team will have to make for themselves.